The development of highly efficient technologies such as solar energy are highly priority nowadays. Solar energy can be converted directly into electricity by solar cells. Dye-sensitive solar cells are emerging as an important options due to their affordable cost, simple manufacturing process, favorable conditions, and high conversion of solar energy to electricity in a very efficient way. The operation of the dye-sensitive solar cell is as follows. Sunlight falls on the surface of the cell, the anode. The electrons found in the organic ink immersed in the zinc oxide nanoparticles are excited and pass their way through the circuit until feeding any devices that requires electricity. The same electrons flow until they reach the part of the counter electrode, which play a fundamental role in promoting the transfer of electrons from the external circuit back to the electrolyte, catalyzing the reduction of the redox electrolyte. And this is where the platinum film is usually found. However, we use doped carbon nanotubes for their efficient catalytic activity and especially for the low cost to require their manufacturing. The electrons use the nanotubes as a catalytic bridge to pass the electrolyte, reducing it, and continue through to reach the start site. Three types of nitrogen species have been studied in the graphitic network and have shown that they play an important role in ERR activity, which are pyrrole nitrogen, pyridine nitrogen, and finally the quaternary nitrogen. Once the synthesis was carried out, the soot obtained was characterized by same techniques, showing the typical carpet-like morphology in the carbon nanotubes arise well taken. The another micrography presents the representative theme, the formation of bamboo-type nanotubes is carried out. Typical role reported for the multi-walled nanotubes doped with nitrogen. In the Raman spectra, a considerable increase can be shown in the D peak with respect to the G peak, which indicates a number of defects in the sp2 network, possibly attributed to the presence of the nitrogen for the formation of the doped nanotubes. Afterward, heat treatments were carried out at three different temperatures: 600, 800, and 1000 degrees. We use XPS to confirm the presence of the nitrogen, as well as possible nitrogen species. Indeed, the main species, pyrrolic, pyridine, and quaternary, were present in the carbon nanotubes. It can be seen how the presence of the nitrogen species decreases, with the exception of the quaternary nitrogen, which seems to remain stable. Cyclic polarimetry was performed to evaluate the ERR activity. Clearly, it can be seen how the doped carbon nanotubes prior to the treatments shows an electrocatalytic activity quite close to platinum, taking into account a high nitrogen content. However, when performing the treatments at 600 degrees, there was a drastic decrease in the total nitrogen and especially in the pyridinic species, but the quaternary species had a slight increase. Likewise, a considerable increase in ERR activity was seen for stocks that can compete against platinum. Finally, with the nitrogen carbon nanotubes, a water-based ink was made using a polyelectrolyte. The cyclic voltamperometry analysis show how the peak current density drastically decreased when the polyelectrolyte was added, despite the fact that the density of the carbon nanotubes were the same as the sample without the polyelectrolyte. By lowering the concentration of the nanotubes, the ERR activity is still present, but with very low activity.